Hey everyone, welcome to another edition of Live Code Tuesdays. My name is Sohan. I'm a dev advocate with Fermion, and today we are going to be talking about Py. Not quite 22 by 7, not quite apple pie, but more about Python. And we have a very special guest with us. We have Joel, who's done so much work in the Python WebAssembly space. Joel, first time on Live Code Tuesdays. Welcome to the show.
Thank you. Excited to be here.
Yeah. One of the reasons actually why we're doing this week is a couple of days later, March 14th is celebrated as World Pi Day because it's, well, 14.3. As an in-joke, we sort of thought we'll speak about Python and WebAssembly. There's so much work that's actually gone into this, and Joel really is at the center of a lot of that. So today we are going to be speaking about something he's been working on called Componentize-py. I will put the link and give you explanations, but I'll let Joel actually do the talking and explain to you what it really is. So, Joel, let's get started. Tell us a bit about the background and we'll get into it.
Yeah, so really, it's another story of building or standing on the shoulders of giants. The support for WebAssembly in the Python world is not a new thing. Hood Chatham and others have been working on Pyodide. If you want to run Python in the browser, Pyodide basically works with another technology called Emscripten to allow the Python interpreter to run in the browser, and has been around for years. And CPython, which is the essentially reference implementation of Python, has had WASI support for a number of years as well, thanks to the strong efforts of Brett Cannon and Christian Himes and others. I came to the party somewhat late, but just in time to be able to add support for this new thing we're calling components, WebAssembly components, which are a big part of what it looks like to essentially compose multiple WebAssembly programs together in a meaningful way, and also run them in contexts that may not be browser-based contexts, maybe IoT, maybe serverless, maybe blockchain, you name it. That's kind of the new thing that we're contributing here, is the ability to create components out of Python programs and libraries. And we'll look at what that means. It has a lot of interesting benefits in terms of security, portability, polyglot sort of composition, being able to reuse libraries written in other languages in a way that's I feel quite a bit easier than for the traditional way you did this with C native extensions in Python. So all of that is really excited to kind of dive into it.
All right, awesome. So we're going to do a deep dive on Componentize-py and why it is such a huge improvement from what we've had in the past, and why it potentially could change so many ways that we're actually building in Wasm. Shout out to Mahesh, who's joining us on the stream. Maybe for the first time, Mahesh. Well, in any case, welcome to the stream, Mahesh. Nice to have you here. And yeah, if you have any questions, that's what we're here for. So feel free to put them in the chat. Could be something basic, could be something advanced, we'll try and get to all of them. Joel, yeah, so let's start the deep dive on Componentize-py, right?
Sure. Shall we show my screen here?
Yes.
That might be a good place to start.
Sounds good. Oh, I think we have
right.
Yeah, there we go.
There we go. Cool. So I'm going to sort of shamelessly reuse a slide deck I presented last year at WasmCon. I've updated it a little bit, and we'll kind of go through it pretty quickly. I want to make sure that we keep this relevant and interesting. This goes into quite a bit of detail about how Componentize-py works and why it does the things it does. But if that's not super interesting and we just want to see how to use Componentize-py, we can kind of switch gears into that too. But I thought I'd start here for those who are curious. So, to give the broad context here, it's not just about Python, and it's not just about the web browser, which, for some people, well, I guess for some people it is, if that's all you care about. But, the vision here is that we want to support a lot of different languages, and not just in isolation, but working together, being able to compose, say, a Kotlin program with a Rust program, with a Python program, and be able to kind of reuse software across language boundaries. And then on the other other side here, we have all the different places we'd want to run that software. It could be embedded in a database so that you can have your code close to your data. It could be in a web browser, just because everybody's got a web browser. It could be serverless functions. It could be edge computing, that sort of thing. So there's lots of places where WebAssembly makes sense, thanks to its sandboxing security model and its portability, etc. And we want to make sure that it has a home in all those places. So I'll just, again, we're not going to, slavishly go through every detail of every slide here, but I just want to give a high-level picture of what came before Componentize-py and what Componentize-py builds on. Look at different ways you can compose WebAssembly software. There's multiple ways, including ways that I'm not even going to go into today, and each of them have their pros and cons. Then we'll look at how Componentize-py uses several modes of composition to produce the component that wraps your application. And then if we have time, we can do a demo, very much freestyle. And then we can talk a little bit about next steps in making it even better. So the prior I mentioned before, Pyodide is basically a combination of CPython and Emscripten, and it's a way to be able to run Python code in the browser. And Emscripten has a lot of neat utilities to make it look like a more traditional operating system environment, where you can load libraries and you can read from the file system and you can do all sorts of things that you might be used to doing in a command line app or in a desktop type application, but be able to do that all in the browser. So if you're interested in running Python in the browser, that probably is your go-to project still for the foreseeable future. We do have a plan to support components in the browser, and you can do that today with Jco. The tooling is still, I would say, less mature and less widely supported in terms of multiple third-party libraries than Pyodide is. So we got some catching up to do there. So I would, if you just care about the browser, then Pyodide's a great solution. Emscripten in particular has this neat feature called dynamic linking, where you can essentially refer to a library that you're going to use and load it at runtime via a URL, so that you're not downloading the entire application. Say you've got NumPy and SciPy, it's big complicated dependencies in your application dependency graph, and you don't necessarily want to load them all at once and have that really slow loading time in a web page. So Emscripten gives you a way to essentially load those as necessary, possibly halfway through execution of a program. And this actually inspired some of what we do in Componentize-py. And then finally, as I mentioned before, Brett Cannon and Christian Himes and others have done some great work porting CPython to WASI. That was recently, just a few weeks ago, promoted to Tier 2, which basically means it's going to be an official part of the Python distribution. A release can't happen without it working, which is a big step up from where we were at Tier 3. And then the drawback up till now has been that native extensions had to be statically linked into the Python interpreter, which is, I won't bore you with the details, but it's quite a challenge to do that for something with something like NumPy and so on. It's definitely off the beaten path for what kind of the Python tooling out there wants you to do. And then just really quickly, Emscripten and WASI are sometimes compared. Emscripten and WASI's goals definitely overlap. And this sort of summarizes maybe perhaps the perspectives, which is, Emscripten is about taking existing software, games, command line applications, etc., and make them work on WebAssembly, mostly in the browser. And WASI has that goal as well, but wants to essentially move beyond sort of the patterns and APIs set by POSIX, which is really what Emscripten provides today. And so, that's the recent WASI 0.2 release was very much about moving beyond just command line apps and the traditional POSIX interfaces that they use, and moving into HTTP and cloud APIs, key value stores, that sort of thing.
Yeah.
And then, oh yeah,
Oh, no. I
Feel free
was,
to
I was just
jump in.
about to, like a couple of comments coming in.
Okay,
Interesting.
sure.
Mahesh says, I learned about Wasm recently, so want to explore more. Well, Mahesh, you're in the right place. I'm so glad that you stopped by here. We do the stream every week where we talk about some different aspect of WebAssembly. I think last week we did something about Leptos. 2 weeks prior, we did something about .NET and WebAssembly. So yeah, stick around. We do this every week. And yeah, glad you're here. Oh, Bunny is here as well. Hey, Bunny, one of our good friends. And I think this question's for you, Joel. You're probably covering this later in the talk, but something about the compilation experience using Componentize-py versus Rust, right? And how the final binary performs. Is that something we can talk about a little later?
Sure, I can briefly address it right now. The one thing that is not obvious from the get-go that I should point out is that Componentize-py does not compile Python code. That isn't really a thing today. Maybe someday it will be, but Python is just notoriously difficult to compile ahead of time. So it does not compile Python code. So it does not do the same thing that Rust code does. So instead, what it does is it bundles the C Python interpreter, basically compiles the interpreter to WebAssembly, and then of course compiles any native extensions such as pieces of NumPy and SciPy and whatnot, compiles that to WebAssembly, but your Python code itself remains Python code. And so it gets interpreted, it bundled as part of the component, bundled with the interpreter, and then interpreted at runtime.
And that part is done by hand, if I'm not mistaken, right, Joel?
When you say by hand, I mean Componentize-py. It basically, when you run Componentize-py, and we'll look at an example later, you tell it where your code is, your Python code is, and it will get bundled into the resulting component. So there's nothing. When you say by hand, I sort of yes, but also it's a single step, and so you don't need to there's not a lot of work that the programmer needs to do to make that happen.
Got it. Okay. But yes, stick around, folks. We will see a demo.
Sure.
I'm just going to shout out that it's twice in 2 weeks that we have an XKCD reference. I was just commenting a couple of weeks ago that we've done the stream for, I think, 3-4 months, and we hadn't referenced XKCD ever, which seems like weird for a tech live stream. So I think we should keep this going. Right. So yeah, good reference there, Bunny. 10 on 10. Go ahead, Joel.
Sure. Okay, so I'll go through this next few slides pretty quickly. But there's multiple ways you can take two pieces of WebAssembly code and compose them together. So that, say, item A can call a function in item B, and item B can call a function in item A, whatnot. Use them as libraries. So the traditional and really only way up until recently has been what we call static linking. So it's basically just like if you're a C programmer or a Rust programmer, you're perhaps familiar with, you basically are lumping all your application code and all its dependencies into one big binary, and that creates a single WebAssembly module that has everything in it and that has no external dependencies outside of what the host is expected to provide. Which, if you're running in the browser, it would be the JavaScript APIs. If you're running in a serverless, worker, that would be whatever HTTP and key value store functionality that worker host provides. So, there are advantages and disadvantages there. It can provide really optimal code with, zero dependencies, which is nice. And it's very widely supported at this point. It does tend to result in code duplication where you have, if you have a library that you're using, in several applications, they can't really share code with each other because it all just gets bundled together into this sort of opaque blob. And there's also no sort of interdependency sandboxing. So if you've got a third-party dependency that maybe you trust up to a point, but you don't necessarily want to give it access to all your application secrets and all your users' data, there's not really any way to essentially within a single module separate sort of different privilege levels. They all are sort of at the same privilege level. Let's see. And then, in contrast to static linking, if you're familiar with kind of traditional native programming in C, you may have heard of shared everything linking. If you've heard of DLLs or .SOs, shared object files, that's what we're talking about here. And so the idea is that rather than build everything into a single binary, you're essentially building multiple binaries, the main application binary, and then reaching out to other binaries, loading them at runtime to get access to other functionality. And especially security-sensitive software such as OpenSSL, this is a great idea because it may be that OpenSSL has a bug in it that's security sensitive. You don't necessarily want to have to update all your applications on your, on your desktop or on your Mac or your Linux machine or Windows. You want to be able to just update one binary, and then all the other binaries are using that binary, so they'll automatically get the new version. So it's great from a security standpoint. It's also, well understood. It's been around for decades in kind of native software development. On the flip side, again, you don't really have inter-module sandboxing. Anytime you load a library, it has access to all your memory and all your secrets and everything. Not great from a sort of supply chain security standpoint. It's also difficult to virtualize. So if you want to kind of pretend that a library, if you want to basically replace a library with something else that virtualizes it, it's because of pointer passing and whatnot, you still have this sort of shared everything environment where it has access to everything. So there's that. And then finally, the new thing here introduced with the component model is what we tend to call component linking or shared nothing linking, with the idea that each component has its own memory, its own view of the file system potentially, its own privilege levels and access to secrets and so on. And that component, whatever that a given component has access to, it can choose what to share with other components or what not to share. And there's no way that those other components can get access to things that they're not supposed to have access to. And so this has really nice ramifications from a supply chain security standpoint, and from just a debuggability standpoint. There's no way you could by linking to another component, it could crash your component by accessing memory out of bounds or something like that. So it has a lot of appeal. Plus, it tends to be a lot easier to mix components from different languages. You don't have some of this C API you don't have to have a rich knowledge of the C API and how to pass pointers around and how to basically convert from one representation of a string to another representation of the string. The component model sort of takes care of that for you. And the main drawbacks are just that it's new, and so it's not yet widely supported. And so, you might ask, okay, which one of these should I use? I mean, they all have pros and cons. Well, the answer that Componentize-py kind of throws out there is you should use all of them. And Componentize-py, in a sense, will use all of these things as appropriate. And that we've got sort of a diagram here of where we've got these WebAssembly modules that end up being sort of isolated in their own sandbox, but we're able to reuse those modules. So rather than having 3 copies of libc, for example, we could have 1 copy that gets reused in three different components. So you can avoid the code duplication, but also provide the sandboxing that we all want.
That sounds really cool, Joel. So yeah, I mean, folks, if just as a recap, because few people have just joined the stream, myself, I'm Sohan, and we have Joel here talking about Python and WebAssembly, specifically a new launch by the Bytecode Alliance called Componentize-py, which Joel worked on. The in-joke is this week is Pi week, because it's Pi day in a couple of days, because 14th March, hence 314. It's a thing, and so we're talking about Python. Just a bit of an in-joke there, but yeah, that's what we're talking about. Arnav, welcome to the stream. Thanks for stopping by. And yeah, Joel's talking about Componentize-py. So let's get to how it works at a high level.
Yep. Yeah, so this is just an overall diagram kind of illustrating the inputs and the outputs of Componentize-py. This is sort of the general case. In a simple case, you might actually just start with a Python library and maybe a few dependencies, and then feed that into Componentize-py, and it can kind of figure everything out from there. And that's what we use for the Fermyon Spin SDK. We just launched a new Spin SDK for Python a few weeks ago that is based on Componentize-py behind the scenes. And the cool thing about that is the SDK itself bundles the WIT files, which are basically the interface that this component will present to a host or to other components. So it bundles the spin WIT files inside the SDK, so you don't need to worry about, knowing where the WIT files are or telling Componentize-py where to find them. It's all part of the SDK. But in the general case that is illustrated here, you would have some sort of WIT file that you want to tell Componentize-py, hey, my application is going to export these functions and interfaces, and it's going to import these functions and interfaces, and that's going to be sort of the public API of this component that I want to produce. And then you're going to provide a Python file, here we call it app.py, that has the code that essentially implements the exported interfaces and calls the imported ones, and does hopefully something interesting. And then one of the cool things about Componentize-py is it does support native extensions, which is a big part of the Python world. If any non-trivial Python app out there is probably not going to be written in pure Python, it's almost certainly going to have some dependency written in C++ or Fortran. Certainly in the data science world, this is very common. And so Componentize-py will let you bring that stuff. So it'll let you bring NumPy, which is primarily written in C++ and Fortran, to as part of your application. And the way that works is ultimately, usually you'll get a .so file that's already been pre-built. You get that off the PyPI, but just for completeness here, we'll show the full life cycle, which is you start with a .c file or a .fortran file, and compile that using WASI SDK, which is built to compile to WebAssembly with WASI imports, and then excuse me. And then that produces a .so file. And so Componentize-py takes all these things, your Python code, the world that you want to target, and any native extensions, and will spit out a component. And that component will have everything built in. That'll have the CPython interpreter. It'll have your native extensions. It'll have your Python code. And the interface it presents to the world is the whatever was defined in that world that you specified.
Joel, so a question for you. I think for folks who might not be super familiar with the concept of the component model in WebAssembly itself, can you talk a bit about this concept of a world within like a WebAssembly interface, right? Like, what is it?
Yeah, so a world, this might be a good opportunity to take a look at some code real quick. Let's look at an example of a world. So let's see. This is a pretty simple one. So this is one I created a demo we can look at in more detail later that uses NumPy. And it's got a very simple interface. The world that it defines has a couple of things here. First, we have this include WASI CLI command. So this basically just says there's a standard WASI world that's been voted on as at least a preview of a standard that provides traditional command line types of utilities. The ability to get the arguments specified on the command line, environment variables, get access to the file system, have access to the network if needed, all those sorts of things that if you've written CLI apps, you have probably used. So we're essentially defining a world that includes another world that basically you could think of it as extending that other world. We're going to take that world, we're going to export everything it exports and import everything it imports. And then also we're going to add some other stuff. And the other stuff we add is actually pretty simple. We're just going to export a simple function that takes a list of floats and another list of floats. These are going to be, let's call them matrices. We're doing matrix multiplication. So a list of lists you can think of as a two-dimensional table. And then it returns a matrix. And either that or it'll return an error. So that's what this result thing, it'll return an error in the form of a string. And so and we could go look, if we want to, at what the WASI CLI command world looks like. Let's do that real quick. Command. Oh yeah, which itself refers to another world, which is called imports. And this one has the more interesting stuff. It gives you access to the system clock, file system, network sockets, random numbers, various I/O related things, input streams, output streams, environment variables, being able to exit early, standard in, standard out, all that stuff. Basically, if you've written a command line program, you want to use some or all of those things. So it basically, in essence, a world is essentially a list of things that the component is expecting to make use of and provided by either the host or another component. And that's what all these imports are. Or it's stuff, as we saw back in the matrix math case, it's stuff that we are exporting to the host. So we're basically saying, host, if you want to multiply matrices, I'm your guy. Here's how you do it. You call this function, and we could export as many functions as we wanted to here, or we could export an interface that itself defines functions and a set of types and so on. Does that help at all?
Yeah, no, for sure. I think when I was at least first introduced to the concept of the component model and especially in the context of WebAssembly, it took me a while to sort of wrap my head around this concept of worlds, right? And why it's so important to, like components being able to export something in a list, all of that. So, yeah.
Yep. And the other thing I just want to really emphasize here, the design of WIT, which stands for WebAssembly Interface Types, which is what these files are written in, that's hence the .wit suffix, is all about being as portable as possible. So we don't want to write our interfaces in terms of like Python, even if we're hardcore Python developers, we don't want to write our WIT interfaces in terms of Python functions and Python classes, because that's not necessarily going to be portable. If I want to be able to make use of this component from Rust or from I don't know, JavaScript or C# or something, I may not be able to represent the representation of classes, say in C# isn't going to be exactly the same as it is in Python. And if I export my interface as Python code, there's a danger that I will be representing something that doesn't really translate into other languages very well or at all. And so that's the idea with WIT was designed to be from the beginning to be language independent and provide interfaces that can reasonably be represented in a wide range of languages.
Got it. Okay.
So there's that. Let's see. And so here's where we start to get into the details. And, I don't blame you if your eyes sort of gloss over when you start to see some of this, because I geek out on this stuff because I think it's really interesting. I found it really interesting. And that's why I wanted to work on this. Exactly what goes on behind the scenes. Just a fair warning, this is the part you need to understand right here. There's not... if you're just using Componentize-py, you can kind of ignore the rest of it because it's just like you give it some stuff and it spits something out for you. This is what's kind of going on behind the scenes. Again, you don't need to know this to use it. It's just for those who are interested in the details.
We love details here on the stream, Joel. Quick shout out to Juan, who's joined the stream. Juan, in case you just joined, we're talking about WebAssembly and Python, specifically the Componentize-py project. And is it a project? Is it a framework? What's the exact?
Yeah, sure. Project, I guess. Yeah, it's a tool. It's yeah.
Okay. And we're doing a deep dive now. So here's where we're really sort of geeking out to see and to look what happens under the hood. So go ahead, Joel.
Sure. Yeah, and I will mention it's Componentize-py is up on PyPI, so you can pip install it. If you go to the README, I think Sohan's going to share a link or two to the repository. But you can also just it's really easy to install if you've already got Python and pip, so you can start playing around with it whenever. But yeah, so here we have kind of the details of what's happening. When we give Componentize-py a WIT file and a Python code and a native extension. So one of the first steps is we take that world that's defined in WIT syntax and we do this bind gen generation. And so one of the things that the component model, if you hear people talk about it in a technical context, the component model has this notion of lifting and lowering. And so lifting basically is the process of taking a core module function signature and keep in mind, WebAssembly core WebAssembly only has a very, very limited type system. So it's got 32 and 64-bit integers. It's got 32 and 64-bit floating point values. And that's basically it. There's a few other things. There's SIMD 128-bit vectors and whatnot that are lesser used, and there's extern refs, and there's a few other things that I'm glossing over here. But basically, numbers is really all you have. And so, obviously, creating a rich expressive interface from just numbers is kind of going to be a pain, and that's been a traditional pain point for WebAssembly developers. And so, WIT kind of fills this need of, hey, I'd rather than just talk about numbers, I want to talk about strings, I want to talk about records, I want to talk about lists, I want to talk about optional values, nullable values, that sort of thing. None of those things can be expressed directly in core WebAssembly, and so that's where the component model has this notion of lifting. So it basically, there's a component type for a function, like the one we just looked at, where we take a couple of matrices and return a matrix. And basically that function essentially gets lifted from a component model version, which deals with these numbers. And so there's this, what's called the canonical ABI, application binary interface, that is used to essentially convert from in-memory buffers to these to matrices, or from in-memory buffers to structures defined in WIT files. And so that lifting process is what this is doing what we're doing at this stage. We're generating WebAssembly code that basically can convert from kind of the low-level WebAssembly representation into a higher level representation, in this case, a Python representation. And then the converse of that is lowering, where you basically have a high level representation, say a Python list or a Python class, and you want to convert that down to what's called the canonical representation in terms of bytes that reside in WebAssembly memory. And so we're generating the WebAssembly code that can kind of go back and forth between kind of this low-level representation and the high-level representation that Python programmers want to work with. So that in your application code, you're just dealing with lists and classes and the usual things. So that's what that does. And then we also bundle together, I mentioned earlier, we have a copy of the Python interpreter. Python interpreter depends on libc to access POSIX style functionality. It's got this runtime.so, which is this thing that specific to Componentize-py that essentially provides helper functions that operate in tandem with this generated code we just talked about to facilitate converting between the low-level representation of types to the Python representation. And then we also have this adapter, WASI Preview 1 adapter. This is sort of a temporary thing as we're transitioning incrementally from WASI 0.1 or Preview 1 to WASI 0.2, since there's a lot of code still that just don't understand Preview 1. There's an adapter to essentially translate that to Preview 2. And eventually that'll go away once everything's been moved over to WASI 0.2. Then we take all this stuff, we generated some code, we bundled some code, the user provided some code, say they're numpy.sos, and we're going to take those all together and do this, what you would call this pre-link, which, excuse me, essentially creates a WebAssembly, basically combines all these modules together into a single component, or at least it gets ready to do that. And part of that process is actually creating a couple other synthetic modules, which essentially orchestrate initializing all the other modules. So each of these modules, libpython, libc, and so on, they have their own little sort of initialization routines that they need to run. Python wants to load all the environment variables so that if an application asks for them, it can access them via an array of variables. So we create this init.wasm that basically initializes all the other .so files. And once we have that, then we take both the synthesized modules, the generated code, the bundled code, the code provided by the user, and then we finally link that into a single Wasm file, which I'm calling uninitialized component here, which it's this component will work, and it's ready to go. The only drawback is that all that initialization I was talking about before, that takes some time, and you don't necessarily want to have to run that every single time you run your application. Ideally, you want a really quick startup, that's, especially if you're running a serverless function, or you're just going to be instantiating and running this thing many, many times for each incoming request. You don't want to have to do that initialization every time. And so the next step we do here is what you might call initialization or pre-initialization, where we take all this stuff that we've generated so far, including a virtual file system, basically all the Python code that your code depends on, and also the standard library code from the CPython distribution, and we make that available during pre-initialization. And so this gives both all the libraries that we're using in this component a chance to initialize themselves, and your application itself to initialize itself. So any code that's expensive to do, but you only want to do it once, you can do that ahead of time at build time, so that when at runtime, it's already been done. We take a snapshot of the result of that initialization, and then and then that snapshot is what we actually deploy to, to the web browser, or to Fermi Cloud if you want to, or wherever else. And then that thing, because the initialization has already been run, we've got basically potentially millisecond or sub-millisecond level startup times. And that's what cold start times, that's what makes cold start times so efficient, is this pre-initialization step. Any questions or comments on that? Oh, my sound is not working great. Hold on. I think someone's talking, but I can't quite hear. Sohan, is that you? Okay. Is it my sound? Testing. Yeah, I can't hear you, Sohan. I barely, almost, sort of hear you. Let me double check my audio here. Yeah, my audio's working. Oh, there you go.
Yeah, it's probably mine.
Okay, yeah, you sound great now.
Okay. I know. Technology.
Yeah.
No, I was just saying, Joel, I'm always in awe of the sort of depth of your knowledge in all of this. So it's great that you're sharing with us. Folks, if you have any questions, please feel free to put them in the chat. And Juan, thanks for joining the stream again. Joel, so one question that I often get when I do sessions and things, right? And when I especially talk about languages like Python and JavaScript and Wasm, is the performance aspect itself.
Yeah.
Right.
Yeah.
And the most common question I get is, hey, how would you compare like a performance of Rust versus Python on WebAssembly? And can you talk us through a bit of that? Does that change with Componentize-py? All of this stuff is also happening compared to, say, a lower level language like Rust and C.
So, I mean, there's sort of good news and bad news there. The good news is what I was just talking about, which is we rely heavily on pre-initialization to make sure that any code that needs to run before the business logic proper, the actual process of handling an incoming request or doing whatever thing that you were asked to do is, that can essentially get folded into the build time, so that you have a snapshotted version of the result of that computation, and you don't have to do that computation every time you run, you call an export and that sort of thing. So that's really cool. And so it eliminates especially this traditional server. If you've been in the serverless world for a while, you know that the pain point has always been sort of the boot time, the cold start time, and so that's what we really addressed head on. Now, for the bad news, like I mentioned earlier in the stream, Componentize-py does not compile Python code. It's just embedding the interpreter, and the interpreter interprets the Python code as usual. And the interpreter, when compiled to WebAssembly, is actually has a slight performance penalty compared to when it's compiled to, say, x86 or ARM code. Because with x86, you can play some tricks. There's if you've heard of threaded, if you're a big programming language nerd, you may have heard of like threaded interpreters or computed goto. These are all sort of techniques that advanced interpreters use on native architectures to kind of provide the best performance possible for that interpreter. WebAssembly, because of its sort of security model and its sort of validation model, doesn't provide computed goto, and so what that means is some of these optimizations you'd use in native code don't necessarily apply. That said, traditionally, you don't use Python for performance. If your performance is your main priority, you're not using Python anyway. So so you get a 20% performance hit, say. I don't know, I haven't really benchmarked it recently, but go into WebAssembly. Generally, traditionally, I mentioned this earlier, if you've got a performance problem in Python, you usually solve that by using something like Cython or Cython, which compiles Python code to C code or to C++ code, or you just use C or C++ or Fortran directly. And that's why so much of the data science world is really not pure Python. It's Python, a Python veneer on top of a bunch of C++ code, etc. So, in practice, if you have a hotspot, you probably don't. You can still use Python, but you probably don't want to do a lot your advanced number crunching in Python, and that's true whether you're doing WebAssembly or not doing WebAssembly. So that's part of the answer. And yeah, so if performance is both from a cold start perspective and from a kind of a number crunching throughput perspective, if that's your priority, you probably do want to stick with either Rust or at most Python code on top of Rust or on top of C code.
Okay, and I think that's, first of all, a great answer. I'm totally going to use that when people ask me. Since we were talking about polyglot programming, I think there are a couple of questions here. One is Bunny agrees and says your depth of knowledge is really admirable, Joe. Yeah, so completely agree there. Which is from Juan, which is, great to hear some tips on polyglot repos, right? I understand imports and exports, but concatenating during dev seems weird. And Bunny is also sort of agreeing, saying, they played around with the concept, but it does feel messy. And admittedly, it is something new, right? I mean, we're so used to doing like an app or a program in like a certain language and having that repo in that language. But now I think with WebAssembly, it's almost a new paradigm, right? And the component model. So yeah, do you have any tips there, Joe?
Yeah. Well, there's a couple things there. One is that the tooling right now for doing, I think if I understand the question correctly, it's a little bit awkward to essentially compose WebAssembly modules where you're kind of doing this at build time. You're taking your Rust module or your Python module and you're composing them together as part of your build process. And so maybe part of the question is, wouldn't it be nicer if you could kind of figure out later in the process, say when you're deploying or when you're running the application, basically how you want to compose them. And this is something that we've been thinking about certainly at Fermyon, and in the context of Spin, we want to make it easy for you to be able to say in your Spin toml, hey, I've got these three components and I want component A to be able to call into component B, some function in component B, and I don't necessarily want to create a component D that actually statically combines them all together. I want to just be able to keep them separate, but then tell the host how to combine them, so that it's just one less step I have to do at build time and whatnot. So that is something we're working on. Brian, I have trouble Hardock and Ryan Levick and others at Fermyon and other people outside of Fermyon have been working on improving this. And if you've heard of the WAC project, it's Peter Huyn from Fastly has been kind of spearheading this, and Brian Hardock has been helping out with it. It's essentially a new language for combining components. And the idea is that we could essentially embed a variant of this language in spin.toml. So we're working on that. Yes, I completely agree that the tooling is not kind of where we want it to be, and we're kind of in between tools. It was Wasm Compose, that was the hot thing for a while, and now it's WAC. But WAC is still somewhat immature. It's still kind of experimental. So it's going to get better. Right now, it's sort of like you might think of it as like a technology preview a little bit. The one other thing I did want to mention on that topic is that one of the projects Ryan Levick has been working on, one of the things he's passionate about is dynamically getting access to components and being able to essentially, treat components as if they were almost like dynamic, Python modules or something like that, where you could have a REPL. He's got this thing called a WEPL, which is WebAssembly eval print loop, where you can kind of just take an arbitrary component and you can load it up and you can start making calls to it, just live, the way a Python developer would use a REPL, and extending that further, basically this idea that you could sort of discover, load a component dynamically and knowing nothing about it ahead of time, see like what functions does it export, and let's look at the docs for those functions, and oh, that looks interesting, I'll go ahead and use that. So creating a more dynamic, less static experience for components is also on the wish list for a lot of people, and the to-do list for people like Ryan. So I guess to summarize all that, I would say stay tuned. We're working on making it better. Yeah.
For sure. And in general, I think the component model in WebAssembly is, of course, it's in a state of evolution, but it's fairly new as well. Juan sent a message saying, my confusion's between Wasm modules, not actually the host module. Okay, so just to confirm, Juan, so you have like a program, say it's written in Rust, but you need like a YAML parser, which is or say it's written JavaScript and your YAML parser is in Rust, and I know you have a date format in Python, and those are 3 different Wasm modules. Is that the shape of what you're talking about? Perhaps, right? And in that case, do things change in like a repo or like things, Joe?
Yeah, I want to make sure I'm understanding the question. Is between Wasm modules. So first of all, I think I mentioned this earlier. Composing WebAssembly core modules, and this could just be a terminology thing where we're not quite using the same words for the same things, but core modules don't really compose well at all. Because they each there has to be some sort of ABI, some way they can kind of talk to each other via high-level types, and that's what WIT and the component model is about. So, but it is certainly true in the scenario that you were talking about. Say you have a Rust library that is built as a component, and you have some JavaScript thing that wants to use that, call into it. The idea there, whether this is the ideal user experience and the one that we want to end up with or not is another question, but is that you would write a WIT file representing the interface that the Rust component is going to export to the JavaScript component, and then the JavaScript component would import that interface, and the Rust component would export that interface. Once you've created those components, then using either WAC or Wasm Compose should be easy, depending on I guess it depends on how complicated this interface is. But we have some examples, say the spin file server repo on the Fermion GitHub repo has some examples of cross-language composition. The WAC repo has some examples. The Wasm Compose repo in the Bytecode Alliance.
Juan, so I think maybe if I'm understanding Juan's question, which is I like to picture the typical FAS lifecycle.
Yeah.
And Juan's also mentioned, but you can choose a language for each little function.
Yeah, for sure.
Like maybe this is what I'm picturing, right? So in your front end, you have like a calculator, and you have like a plus, whatever, addition, subtraction, division, multiplication, and each of those is its own, say, FAS function, right? Or each of it's its own function, and you could potentially write them in different languages. So your calculator app in itself is completely polyglot, and they're sort of working with each other. That is like a realistic scenario that can be implemented even right now, correct?
Yeah, I mean, especially if you're using Spin, you can have multiple. You can within a Spin application, you can have multiple components, each given its own endpoint. So you could have /multiply and /add and /divide, and say you want Python to do the multiplication and Rust to do the add and JavaScript to do the divide. You could do that today. No special tools really needed. Just Spin.
Exactly. Yeah. Yeah, I'm still trying to, I think, fully understand how. So you traditionally use API routes in full stack JS project. Yes, that is true. Now you can code router in one language, then the auth handler in another one, and yeah.
And yeah, this sort of, especially if you're doing the router. So now it's almost like there's two dimensions where you can kind of cut. You can cut the concerns. You could have it route by route, or you could say the router. So it's almost like horizontal versus vertical. It's like route by route by route in the vertical axis, or like more vertically say, I'm going to do all the routing in JavaScript, and I'm going to do all the auth in Python, and I'm going to do all the DB fetch, in Rust. So there, that is kind of where Wasm Compose tends to shine, or WAC, where you should be able to do that as long as you have clearly defined interfaces between each of these stages. So the router is going to presumably present just a WASI HTTP interface to the host, but then when the host gives it a request, then it's going to extract some stuff. Then the question is, what kind of interface is it going to use to talk to the next layer in sort of this sandwich, which is, I guess, the auth layer. And that could be some standard WASI interface, WASI HTTP again, or it could be just one that you make up and you write your own WIT file for. The one caveat there, and this actually might be a good segue into the thing I'm really passionate about these days, which is doing composable I/O, composable concurrency. That's one weakness in the current version of WASI that we're intending to address in WASI 0.3, which is if you set up your application, if you compose your application that way, where you've got the router component and the auth component and the DB access component, only one of them can actually do I/O at any given time, and so that could be a problem if auth needs to do some sort of like call out to some third party, but say it also wants to kind of maybe it decides, oh, actually this thing doesn't require authentication. This is getting a little contrived because obviously it wouldn't send anything in reality to the DB layer if it hadn't finished authentication. So but say it needed to for some reason. Then that could be a problem but having component C talk to the database concurrently with component B talking to an auth server could be it's a challenge right now. It's not impossible, but it's impractical, and that's something that I'm working on. And I've got a fork of Componentize-py that actually demonstrates this the sort of I/O concurrent composability. But that's something that we're working on, and over the next few months, I'm hoping to flesh out and move from the experimental phase to something that people can use.
Awesome. And keep those questions coming, Juan, if you have follow-up questions. I think hopefully we've sort of answered, the questions that you had, but yeah, feel free to ask follow-ups. Joel, you said you did want to speak about this concurrent thing that you were working on, right? I know how much you're allowed to speak about, given that it's also, an ongoing project, but yeah. Now would be, a good time.
Yeah, let me, shall we share my screen one more time here?
Sounds good. And a few folks just joined in. Yeah, we talked about Python and WebAssembly, specifically the Componentize-py project. I'll link it right now. It's a project by the Bytecode Alliance that Joel here has done a lot of work on. We've just done a deep dive, really looking under the hood of how Python and WebAssembly works. So yeah, we're going to continue that conversation.
Cool. Let me make the font a little bigger here.
I love the name, Joel, I must say.
Yeah. So it's an acronym for Async, you sync, we all sync for async. I thought that was mildly clever. I was pretty proud of myself. But basically, so this is, in a nutshell, an experimental polyfill for what we think WASI 0.3 will look like. And again, keep in mind, it was only a month or so ago that we released 0.2. So this is not imminent. I'm hoping by the end of the year. Don't hold me to that. I'm sure things always seem easier before you dive into them completely. But my personal goal is to get WASI make the distance between 0.2 and the 0.3 release much smaller than the 0.1 to the 0.2, which took, I think, like 5 years or so. I don't want this one to be 5 years. I'm trying to, as much as possible, accelerate the process of getting to 0.3, because I think it's going to be so powerful and important. And one step on the way to that is creating a polyfill that allows you to play with these real 0.3 features in a way that still is compatible with hosts that are based on 0.2. And so you can play around, you can check out the repo and play around with it. I need to actually expand the README to kind of give you a little get started guide. I do want to emphasize that this is still experimental. I don't recommend you build anything serious on this. I do want feedback though. So if you're, willing to approach it with sort of like an experimental mindset, that'd be great. But the basic idea here is, like I said, create a sort of a preview of what WASI 0.3 will look like. And as an example of that, you can see a few examples I have here, but one example I created here in both Rust and Python is a pair of components which are essentially doing a middleware composition, kind of similar to what we're talking about with Juan, where we are doing concurrent I/O, and in particular, we want the middleware to be able to essentially handle encoding of request and response bodies and take care of, say, compression transparently. So you've got some sort of service component that does some business logic, but you don't want to make that component responsible for understanding how to deflate and inflate, to name a common compression algorithm, the request and response bodies. And so that's what this middleware does. So the idea is that you create the middleware that knows how to do the encoding and decoding, and you have your service, and you can compose them together. And you can and the interface that composes that they use to talk to each other is just WASI HTTP. It's the same interface they're using to talk to the host. And a diagram would help here, but I'm afraid I don't have that. But the basic idea here is the host calls the middleware, WASI HTTP handle, which gives it a request and expects a response back. And middleware basically takes that request, wraps the incoming body, if there is one, the request body, in something that does the decoding on the fly in a streaming manner, passes that wrapped version to the business logic. The business logic just sees the decoded, the decompressed bytes, does whatever it wants with them, then produces its own unencoded bytes, sends them back to the middleware, and that middleware then wraps that response body in something that I should say encodes. In other words, compresses the response body and then streams that back to the client or back to the host, which presumably is talking to a client. And so that's really cool. You can't really do that in any remotely ergonomic way with WASI 0.2, which is a shame, but you will be able to for 0.3. And if you want to see what that looks like, you can take a look here. I guess we could even click on that. This is the sort of thing you probably want to look at your leisure. I think we're running out of time here, but it's all up there. You can run the tests. It all works. There's a lot of code because deflating and juggling input streams and output streams just has a lot of code, but it's all pretty cool.
Yeah, I'm just going to link. Is it pronounced Isyswasva or?
Yeah, I guess so.
Okay.
I mean, I made it up. We can pronounce it however you want.
I hope that sticks. Yeah, Isyswasva. It rolls off the tongue. Yeah. So yeah, check it out, folks. Here's the link. This is on Joel's GitHub. As he mentioned, it's a sort of fork of Componentize-py, but with some of the async stuff there. And thanks, Juan, for that question. I think it drove some really nice conversation. Yeah, other A's are silent in ISIS. Okay. Cool. Remove that. Where next for, you were mentioning next steps, or where next for the Python ecosystem within WebAssembly, Joe?
Yeah, well, again, I'm super passionate about this composable composition. I think it's going to unlock a lot of meaningful use cases, especially in the middleware serverless arena. So that's what I'm going to be focusing on for the near to midterm. The other thing is there's various issues open on the Componentize repo. If you look at the contributors, it's been mostly me. A few people have submitted very valuable PRs, but it's mostly me, like, opening a PR and then approving my own PR, which is not like great software engineering practice. So I would love to see other contributions, and would be happy to mentor folks who are, want to help but don't know where to start. That would be great. There are just various ease of use things. One big thing that I'd like to see Componentize-py do is be able to automatically download dependencies, possibly just by shelling out to pip, but from PyPI. So it sees, oh, it looks like your requirements.txt say you need NumPy and you need the toml package, or etc. I'm going to go out and get those for you. You need to use pip to do that. So try and make the user experience better. And there's various ways. Again, the issues are on the GitHub tracker.
Nice. Yeah, folks feel, and you just heard Joel's offer there. He's happy to mentor folks as well. So yeah, if you can, it's all open source. So if you can, get into the repo, try your hands out at a few of the things that he mentioned, that would be amazing. I think we have time for a couple of questions that have come through, Joel, and one is from Akan. Welcome to the stream, Akan. Thanks for joining in. Akan says that's all like using different languages to handle different modules by different developers on the same app. Right? I think I'm going to add to that question, saying, does the component model sort of open up the idea of different people with different sort of skill sets working on like the same app, right? Like the two of us, I know TypeScript, like Python, we could potentially, So is that like one of the, consequences?
Definitely, yeah, and and not just people with different skill sets, but possibly different skill levels. If you've got a junior developer on the team who, just because, and we've all been there. Even if you're a senior developer, you were a junior developer once, and it's an important step in your career. You can't skip it. But you might, the junior developer might, have be responsible for maybe a less critical piece, and because of the sandboxing model that the component model provides, there's no danger of a mistake made by that junior developer bleeding into other components. At least not in a way that would not, I guess I should say, if the components are talking to each other, obviously, the worst that could happen is that component could give the wrong answer, but it's not going to crash and bring down the other one, in a way that it would if it was sharing memory and basically it was no holds barred kind of sharing. So yes, I think that is true, and also I want to emphasize that this isn't the first technology enabling polyglot, composition. Mm-hmm. It just, in my opinion, is one of the easier ones. Given that it is provides the shared nothing boundary, and if you get a chance, check out. Luke Wagner is doing a presentation here in a couple of days at Wasm.io, kind of illustrating examples of that. So yeah, I think it's really cool for that, for multiple developers and multiple skill sets.
Yeah, great question, Akan. And and Luke also one of the co-creators of WebAssembly. Maybe is that Yeah, and Wasm.io is happening in Barcelona on Thursday and Friday this week. Sneak peek, Fermion does have like a big announcement coming there, so keep your eyes peeled on social media, Discord, YouTube, whatever, and you will hear about it. Couple of things. So Juan asks, would be cool if you could share one day the dev experience of communicating between modules. Yeah, I think Joel would love to have you on a future stream where some of the tools that you mentioned will be in a slightly more evolved state, where we could maybe do a demo of, like these modules talking to each other as well. Mm-hmm. And since we are almost out of time, quick shout out. Yes, big announcement coming this week. Next week, Thorsten, Hans, and myself will be live streaming from KubeCon in Paris. So we'll do a bit of a walk in the expo floor, maybe, but we'll also talk a little bit about the announcement. So please join us for that. We will be streaming live from KubeCon, so expect some internet issues and glitches as well, maybe, because we're streaming from like a public place, but also you'll get a sense of how KubeCon is shaping up. Big event, one of the biggest tech events in the year in the cloud native space as well. Thank you everyone for joining in. Bunny, Juan, Akan, Mahesh, few others who I might have missed. Always awesome to have this crowd. And most of all, thank you, Joel, again, for this really deep dive into Python. We're definitely going to have you back on the show to talk about some component stuff as well, right? So yeah, thanks for joining us.
Yeah, thank you.
Cool. All right, folks. I will see you next week. Again, same time, same place. And we will be streaming live from KubeCon. Until then, yeah, check out things. And yeah, thanks, Akan, for your kind words. And we will see you next week. Take care now.